Hello everyone. In this video, I want to talk about how one takes the time derivative of a rotation matrix. Now, rotation matrices are special matrices, they're orthogonal, and so taking the derivative of one with respect to time requires some special considerations. And in order to handle this, we're going to introduce a mathematical tool known as the matrix exponential, which is something I find very useful in a lot of the projects that I work on. So let's get going. Here's the setup for our problem. We have a point x, and x is actually going to have a position in 3 dimensions given by the scalar values x, y, and z. And I've drawn just a 2D axis here, and you can imagine that the z-axis is just coming straight out of the slide towards you. And we're going to move this point x in space over some amount of time delta t by applying a rotation to it. And the total amount of rotation is going to vary over delta t, and this is going to create this arced trajectory. So here's our rotation matrix, and the question that we want to answer is what is the velocity of this point x? And of course, velocity is equivalent to taking the time derivative of this function. So here's our position of x, and we can take the time derivative of this equation. Now, of course, the only thing that's varying in time here is the rotation. So the time derivative of x, the velocity of this point x, is given by the time derivative of this rotation matrix. And now we want to come up with a succinct formula for this time derivative. And we're going to do this in 3 steps. In step 1, we're going to introduce a physical quantity called the angular velocity, and this is going to be given as a vector, omega. In step 2, we're going to come up with a relationship between the angular velocity omega and the rotation matrix R. And then in step 3, we're going to produce a general formula for the derivative of R with respect to time. So only 3 steps, not too bad. Let's get going. And we'll start by deriving the angular velocity. Here's our modified problem setup for working out the angular velocity. We have our point x. I've introduced an as yet unknown velocity vector v, which is a 3×1 vector and will be equal to x dot. And we know that because x moves by rotating, and here without loss of generality, I've chosen for x to rotate around the origin, that x is going to travel in a circle. Now we can generalize this idea even further by introducing an axis of rotation, here given by the unit vector a, that describes the plane in which x is rotating. For our simple problem setup here, where x rotates in the xy plane, a is just the z-axis, but of course you can tilt a and have x rotate in any plane, and we're going to take this into account when we do this derivation. Finally, we're going to introduce theta dot, which is the time rate of change in the angle theta around A with which x is rotating. So you might think that this is actually the angular velocity, but we're going to see that the angular velocity is not much more, but slightly more complicated than just this. So armed with this problem setup, let's get going. I said that the vector v was an unknown vector, so let's try and make it known. We're going to describe this vector using a direction given by the vector d here, and a magnitude, which is given by the scalar quantity alpha. And we want to find values of each of these things that will relate them to our rotation axis A and our angular change theta dot. We can tackle this one at a time, and I think it's easier if we start by working out the direction B. Well, we know that our point x is rotating around the axis A. This means that this rotation can't change the value of x in the direction of A, which means that our velocity has to be orthogonal to A. We can also see via the scientific method of looking at this diagram that if the motion of x, v, had any component along the position vector, so this is the vector that points at x from the origin, then x would quickly fall off its circular trajectory. And since it can't do this by construction, it means that x can have no component of its velocity along its own position vector. Or in other words, that the velocity is also orthogonal to x itself. So we need to find some vector d which is mutually orthogonal to both a and x. And of course we can do this by using the cross product. And here we have to normalize our cross product by the magnitude of the position vector x in order to ensure that it has unit magnitude, which makes it a true direction vector. So that gives us our direction d, and now we need to figure out what our magnitude alpha is. We're going to introduce a new point, a new vector y, and y is just going to be our original position x plus our unknown velocity times a small increment in time, delta t. And we can substitute in our previous formula for the velocity, alpha d, and this gives us the following equation. Our goal is to relate this small offset to a tiny change in the angular displacement of our system. In other words, we can look at what happens to our vector x if we rotate it by an angular displacement given by theta dot delta t. And we can intersect this line with our new point y. And now we can ask ourselves the question, what value of alpha will make this diagram consistent? Now to do this, we're going to rely on every mathematician and computer scientist's friend, trigonometry. And by looking at this diagram here and exploiting the fact that we know that the velocity is orthogonal to our position vector x, we can arrive at the following equation for the length of our offset. This tells us that alpha delta t is really equal to the length of our vector x, the length of the adjacent side of this right triangle, times the tan of theta dot delta t. And it's going to make our lives easier if we break up this tan operation into a sine and a cosine, which we've done here. So here's that formula again. And now to finish everything up, we're going to remind ourselves that delta t here is really, really tiny. So if delta t is really, really tiny, then theta dot delta t is also really, really tiny. And we can exploit the identities that the sine of a tiny number is just the tiny number itself, and the cosine of a tiny number is equal to 1. Substituting this all back into our approximation shows us that alpha delta t is really equal to the magnitude of our position vector x times theta dot times delta t. We can divide out the delta t's from both sides, and this implies that alpha is really equal to the magnitude of x times theta dot, which is really nice because now we have an equation that relates alpha to the angular time rate of change. Now we can substitute in our new definitions of alpha and d, and this gives us the following equation. Now we can cancel out the magnitude of x, and we wind up with something quite elegant. What we're going to do is, because theta dot is a scalar, we can group it together with the unit vector a, and we can call this whole thing the angular velocity omega. So the angular velocity vector is a vector that has a direction pointing in the axis of rotation, and the magnitude of this vector is the time rate of change of the angle around this axis. And this brings us to the end of the first chapter of this story. So let's move on to chapter 2. And here we're going to focus on finding a relationship between this angular velocity vector and the rotation matrix we were interested in before. So here's our setup again. We have the derivation of the angular velocity, which is this funny vector which encodes both the axis of rotation and the time rate of change of the angle around that axis of rotation. And we're going to ask ourselves, how does omega relate to our rotation matrix R? So I've rewritten the velocity formula for the point x in a very concise form here using omega. It's just omega cross the position vector x. And we're going to start out by applying a useful algebraic identity. One of the nice things about cross product is that it actually has a matrix form. So if we take our angular velocity vector omega and we write it using the following skew-symmetric matrix, and I've indicated the operation of transforming the angular velocity vector to a matrix by enclosing it in square brackets, we can write cross product as matrix multiplication. And if we write velocity as the derivative of x with respect to time, we see that this really gives us a linear ordinary differential equation. And the nice thing about these particular types of ordinary differential equations is that they have analytical solutions. So we can solve this directly to get a formula for the trajectory of x. And the solution comes via a thing called the matrix exponential. So the matrix exponential takes as input our 3x3 skew-symmetric cross-product matrix multiplied by time, and it produces a new 3x3 matrix. Let's go back to where this all started. We had a point that was moving from some initial position in space to a position in space at a new time, and this movement was governed by a rotation matrix, which was changing as a function of time. Well, we've just seen that we can also express this motion using a matrix exponential. And so what this implies is that our time-varying rotation is really a matrix exponential. And this is an incredibly useful piece of information to have at our fingertips. Just before we go on, we should talk a little bit about computing matrix exponentials. Because offhand, this looks like a very complicated detour to have taken. As a review, let's say I give you an n by n matrix A, and A has an eigendecomposition, which means that we can decompose A using an orthogonal matrix V, which contains the eigenvectors, and a diagonal matrix, lambda, which contains the eigenvalues on its diagonal. Then the matrix exponential of A can be computed in the following way, where we exponentiate all of the eigenvalues and then sandwich them between the eigenvector matrix and its inverse. And this should immediately worry you. If n is really big, this is a really expensive operation. So fortunately, there's a very efficient closed form answer to this problem when A is a 3x3 skew-symmetric matrix. And it comes to us via a thing called Rodrigues' rotation formula. Let's look at how to compute this. We're going to start by multiplying our angular velocity vector omega by time, t. And we're going to do this in sort of a funny way. We're going to break omega up into the axis of rotation, which is just normalized omega, and the magnitude of omega times t, which is the amount we're going to rotate around A by. And we're going to use this to compute Rodrigues' rotation formula. So given these two terms, you can show that the matrix exponential of a skew-symmetric matrix can be expressed using the following formula. And here, the square brackets are our cross-product matrix operation. So we take our 3x1 axis of rotation, which we've computed from omega, and we transform it into a skew-symmetric matrix. And we multiply it by the sine of our angle of rotation theta, and also by 1 minus the cosine of our angle of rotation theta. And now, thanks to the Rodrigues rotation formula, we have a really slick way of evaluating these matrix exponentials quickly and converting between angular velocity vectors and rotation matrices. So we're going to use this a lot. It's a really, really powerful tool. It's a good thing to have floating around in the back of your mind. Now that this little detour is over, let's return to what was essentially the problem we started with, which was, what is the time derivative of this rotation matrix? Well, actually, we've already seen the answer to this. And that answer starts with the fact that we actually know how to take the time derivative of the trajectory of our particle x. We saw that that was just equal to this skew-symmetric angular velocity matrix times the position x itself. Well, comparing these two formulas, we see that this implies that r dot is really just this skew-symmetric angular velocity matrix. So we take our angular velocity vector and we stuff it inside of a skew-symmetric matrix. And this formula gets us most of the way there to answering the question we set forth at the beginning of this video. We just need to do a little bit more work to come up with a slightly more general formula. And that's going to form the focus of the third chapter of this little mathematical novella. As usual, we return to our standard setup. Our particle x is rotating, so it starts at some position at time t, it rotates to a new position at time t plus delta t, and it does this according to some angular velocity vector omega. The final question we want to answer is, what is the right way to compute the rotation matrix derivative when there's a whole bunch of previous trajectory for which the angular velocity did not equal omega. So we have this rotating particle. It's always rotating around the same circle, but it can be speeding up and slowing down. So let's see how we do this. So to do this, we're going to build an explicit formula for the point x at t plus delta t. And we're going to do a bit of a funny thing. We're actually going to fix the time point t. This is our initial condition. It doesn't change. But as we vary delta t, the amount of time that's passed since our point reached x at t, we're going to get different displacements. Now, if we have some initial starting point x0, we can rotate it by some rotation matrix that brings it up to x at t. So here's our start point. And here's all the previous rotations over little segments of the trajectory, all concatenated into a single rotation matrix. And remember that t is fixed, so this is a fixed variable. It's a constant variable. Finally, in order to move our point between its position at time t and its position at time t plus delta t, we'll introduce a new time-varying rotation matrix, delta r. And just like before, we're going to take the time derivative of this whole thing. So here's our velocity. the velocity of our point on the segment between x at t and x at t plus delta t is given by the time derivative of x with respect to delta t. Remember, this was the only variable we had left. We get our standard thing now, which is just the time derivative of delta r times our constant rotation r at t times our starting point, x sub 0. And because we've done a lot of hard work up to this point, we know this. We know what the value of this time derivative is. It's just our angular velocity matrix. So we end up with a formula that takes some initial starting point of the trajectory, rotates it to the current position, and then applies some angular velocity. Now sometimes it's convenient to rewrite this velocity formula. You often see it in a different form, and I want to take you through how we get from what we have here to this other arrangement of the terms. So to start off, we're going to unmatrixify our cross product, and then we're going to reverse the order. So if you have two vectors, c cross d, that's equal to the negative of d cross c, and that's what we've done here. We've switched the order of our angular velocity vector and our rotated start point, and we've negated the whole thing. Now we can factor out our rotation matrix R from the cross product expression. And that gives us something that looks like this, and this is just using standard identities for the cross product operation. And using this rearrangement, we can put this all back together into a more standard form. The way we're going to do this is we're just going to re-express our cross product as a matrix equation. So we bring back our skew symmetric operator, but now it's applied to our initial start point, x0. And we keep our rotations in the same place, so we get this rotation sandwich. And you'll notice that our skew symmetric x0 cross product matrix has become transposed, and our negative sign has disappeared. And this is, of course, because the transpose of a skew symmetric matrix is equal to the negative of the matrix itself. And so we can absorb this negative sign into this cross product matrix by using the transpose. Why do we write this way? Well, this gives us a very nice formula in matrix notation for the velocity that is linear in omega. And especially in the sort of physics-based animation world, this can be very convenient going forward. So what did we learn? Well, we learned three things. The first thing that we learned was that a rotation can be expressed as a matrix exponential, where the angular velocity vector is equal to the time rate of change of the angle around some axis A. And both these pieces of information are stored in the angular velocity vector omega. We learned that the time derivative of a rotation matrix is just the skew symmetric cross product matrix built using that angular velocity vector omega. And then finally, we learned this very nice formula for the velocity of a moving particle that was in terms of the angular velocity vector and the current rotations of the point. These three things taken together paint a pretty complete picture of the time derivative of a rotation matrix. So I hope you found this interesting. Thank you very much for watching, and hopefully I'll see you back next time.